So where we stopped off last time was looking at importance sampling and how you choose the density for the proposal distribution. And we saw that you can choose good densities that make life better for you. You can choose bad ones that make things even worse for you than just using crude Monte Carlo. We saw that there's this one here, which is an theoretically perfect optimal density, which I've been calling G star, but you can't in practice use it because you need to know the thing that you were trying to estimate to use it. So we'll quickly look at the next best thing, which is to say, instead of looking at the theoretically best case density out of all possible densities, we'll just restrict ourselves to a specific family of distributions. So, for example, we might have a problem and we want to use importance sampling on it, and we want to only use normal distributions as the proposal densities. And we want to ask, what's the best possible normal distribution that I could use to do as the proposal density? So that's what I've written here is the parametric variance minimization problem. So you choose some family of distributions with density f, semicolon, and then some vector, which is the parameters which define the distribution. So if we were doing normal, then normal variables, then this might be a vector with the mean and the variance inside it. And we want to ask ourselves, what is the vector of parameters, the mu and the sigma squared, which minimizes the variance of importance sampling estimator when we're looking at the variance. So this can be simplified a little bit. So this is just writing out in here the definition of the importance sampling estimator. So the variance of indicator x is greater than gamma, and then the likelihood ratio, the original density f evaluated at the point x, divided by the new density here, f of x, which is the parameter v. So I'll try to keep f of v written here as well. So we can simplify this out. The variance of anything is its second moment subtracted away the mean squared. So we'll use that same formula here. So the optimal vector is looking over all vectors v that minimize expected value of this thing squared. So the indicator squared, it just is itself. When it's 0, 0 squared is 0. When it's 1, 1 squared is 1. So that doesn't change. This part does. So we get the original density f of x is squared. And then divide through by the proposal density with parameter v squared. And then subtract away the expected value of, so instead of writing it in long form, I'll just write over here the IS estimator, the expected value of that squared, because that's what we're actually dealing with. So this here is you can, because this thing is a Monte Carlo estimator, it's unbiased, we know it's mean, it's the thing we're trying to estimate. So that's just equal to L squared. And there's no V's inside there at all. So minimizing with respect to this, we can just ignore that part here. and just say we're minimizing with respect to the second moment of the estimator. So where does that leave us? And the last thing we can do is put this back in terms of the original density. So instead of with respect to f of v, do sort of a reverse importance sampling to put it back in terms of the original one, f. So in that case, indicator x is greater than gamma, f of x squared on f of x at v squared, and then multiplied by the likelihood ratio to go from f at v to the original f. So this actually cancels here, so the squares cancel with that new likelihood ratio, and the resulting thing that we try to minimize is just under the original density, the indicator that the rare event happens, multiplied by just this likelihood ratio here. So I've just copied that across.
How can you divide this?
Oh, good. So that's what my terrible handwriting was trying to say. So we're looking for the V star, which minimizes the variance of importance sampling inside this family of distributions. So how you actually solve that minimization problem, that's quite difficult. The one sort of trick that can be used for this is, instead of solving an optimization of an expectation, you throw in some kind of Monte Carlo step here. So instead of minimizing that true value, if you instead sample from the original distribution some xr's, and you try to look at the minimum of the the sample mean, xr is greater than gamma, and then the likelihood ratio of each of them. Original density f at xr divided by the new density at the point with parameter v. So this thing is called the stochastic, I can't spell, stochastic counterpart to the original problem. And this way of simplifying the problem is just called the stochastic counterpart method. And so what is achieved here is that instead of looking at this expectation, which is complicated to evaluate, and then trying to numerically minimize that, we sample from that distribution, and then we pretend after that the x's are fixed. And then the problem is reduced to a deterministic optimization problem, where this is the objective function, and we can just throw that into R's optimization routines. So that has to be done either, as I just mentioned, through the optimization routines or by root finding. And so the equivalent problem there is as you do when you're optimizing, the thing you're optimizing, you take the derivative and set it to 0. So here we'll take the derivative with respect to v, the parameter of this whole thing. The sum from r equals 1 to r of the stochastic counterpart. And so there's nothing to do with the v in most of this formula, so the derivative with respect to v is only really applied to this last element here. So we can sort of drag that through the equation. And so, using a bit of algebra here, there's a couple of lines. You can, using basically the chain rule and comparing it to the derivative of the logarithm, you can simplify this last term, the derivative of 1 on the density, and it turns into something multiplied by the derivative of the logarithm of the log likelihood, effectively. And the reason you do that is that because that thing has a name. It's the score function. So imagine statisticians would have seen that would have popped up in different scenarios, and you know that for most distributions you can just open a book and say what's the score function for the normal distribution, for the exponential gamma distribution, and just look it up like that. So but still there is some problems with this approach. So this was the derivative, and the way you would solve it is setting it to 0. So I'll just write that down. So the problem with this is that, well, to solve this you have to use some iterative algorithm to like some kind of Newton's method algorithm. And it's not like they're particularly slow, but if you needed to do this many times, then you'd feel the time it took to be quite slow. And in our scenario, when we want to look at rare events, we have an even bigger problem, which is the thing we're optimizing. When we take the stochastic counterpart, the indicator here will basically never be turned on. So if we're in the stochastic counterpart problem, we are sampling from our original distribution f, and we're trying to minimize this thing, which each term has an indicator that xr is greater than gamma. And so in the rare event land, gamma is very large, and if all of these indicators are turned off, then trivially you get it's all 0 all the time, and you get nowhere. It says that every distribution is just as good. Useless. So mainly I'm showing you this approach because a lot of the same techniques are in the cross-entropy method, which I'm going to show you in the next slide. But this approach of directly minimizing the variance can be done, but you need to throw in this magic sauce, importance sampling, for it to work at all. And I don't want to go into the details of that because it's going to be pretty repetitive of what the cross-entropy method is doing. So, and this method is paradoxical. I think it took me a long time to understand the details of what was going on with this method. I should ask. I sent around a document, a tutorial on the cross-entropy method. I was wondering, did anyone open it? One person? I thought this would be a rare event. I thought nobody would open it. Okay, so that document is sorry? Yeah. So effectively, I'll try to go through and explain that today. But if there's, just yell at any time if nothing makes sense. So what I'll try by doing is explaining the method at an extremely high level, and then at a slightly more detail, and then at the end get down to the boring mathematics that explains what the hell's really going on. So the method here is, the idea is to find an importance sampling distribution iteratively. So you start out by saying, just choose any proposal density for your importance sampling, and then generate a better proposal density given that, and then generate a better one again, and iterate until you're happy, you get something that you think is very good, and then just run normal importance sampling with that proposal density. So here is just a plot of this in action. So if you wanted to find the probability that standard normal takes the value over 5, that's not a very rare event and not a very hard problem to solve, but just humor me. So if you want to find that, and you want to find the best proposal density within this family here of normal distributions, say which normal distribution will give me the best proposal density for importance sampling, then starting with the standard normal, then all these curves here show the cross-entropy method in action. It says it'll start off with this blue curve, which is the original curve, the original density that I just chose randomly, and then it'll do one iteration and realize that a better proposal density is one where the mean is shifted to the right and the variance is reduced a fair bit. And then from there, it'll decide, next iteration, I can do better again by increasing the mean a bit more and decreasing the variance a tiny bit. And it moves across here until it gets to the blue curve, where it says it's happy. Sorry, that's not blue, that's brown. The brown curve here, where it says this is the best normal distribution you can get. And the way it's decided that is it's trying to get closer and closer to G star, which is that theoretical absolute best thing that you can do. That's not a normal curve at all. It's this weird kind of normal distribution that's been truncated to be greater than 5. So that's what this pink curve is here. That's what you would use if you already knew the thing that you were trying to estimate. You would just use that. But cross-entropy, what it does is it tries to push itself closer and closer to that, but staying within the restriction that it's only going to be normal distributions, or it's only going to be whatever family of distributions you've decided beforehand. Yeah.
Do you have to change both mean and variance each time? Just change variance and then the mean?
So in that example, both were changing every time, but you don't need to. You could choose the family of normal distributions with variance 1 and with flexible mean. That's something on a few slides that I'll do. So the algorithm at its very highest level is to start off just by choosing this family. So you want to look within the family of gamma distributions, or the family of mixtures of Erlang distributions, or whatever you like, any kind of distribution. Just fix it beforehand, and then look at the parameters which will define a specific distribution inside that family. that's what we'll be searching for. The next thing is to just pick any starting point. So, well, I've got V naught here. So in that previous example, I just started with standard normals. It wasn't a great idea, but you need to start anywhere. And then you iteratively construct a better proposal based on the previous one, trying to push yourself closer to G star. So that one is one that's proportional to the original density, but conditioned on the rare event actually happening. So in a sense, cross-entropy has finished its job at that point. Cross-entropy is just giving you something, a distribution, which you'll then go back to normal importance sampling and use that as the proposal and come up with your answers from there. So, some more details. So, when you pick your family of distributions, you pick your starting point. You also need to pick some number R, the number of Monte Carlo replications that you're going to use, and rho. So this is a bit of a strange parameter that I'll explain in a moment. So this is a fraction between 0 and 1. And step 2 is an infinite loop. So you keep inside the loop at step I, you're simulating IID random variables, capital R of them, from whatever your last guess is, your last best proposal density. And then once you have capital R of them, you line them up in order from smallest to largest, and you take a chunk from the top. So if your rho you chose to be 10%, then you look at what point is it that only 10% of the x's are above here, so the 90% quantile, effectively. And this is so gamma sub I. You end up getting a sequence of these gamma sub i's that increases up until the gamma, which is the thing that you care about. So in effect, what you're doing is you're solving not so rare event estimations one by one. So you solve probability x is greater than gamma 1, which is small, so that's not a rare event, and then you solve the slightly more rare event, probability x is greater than gamma 2, all the way down to the really rare event that you care about, probability x is greater than gamma. So step 2, you found your quantile. This is the point where you can quit the loop if you're finished. So if you've realized that your sequence gamma, you're at some gamma I, and that's actually larger than the final value you care about gamma, then you can quit your loop, and what you've come up with is actually going to serve you perfectly fine for importance sampling. So this is where the loop ends here. But if you've just started, that's not going to happen. If you're going to need to update from your previous to a better density. And the way you do that is create this this set of elite samples, which is kind of a hilarious terminology for it. But effectively, you collect, if you've ordered all your samples in terms of their size, so these are the smallest x, the next smallest x up to xr, then you take the top fraction, this ones that are above gamma I, so there'll be rho of them as a fraction of all of them, and you just bring them together into a set E, the elite set. And then comes the part that actually matters. You choose the next parameter, you're stepping closer to the optimal G star by using these elite samples and just doing a maximum likelihood estimate on them. So you solve the problem where VI, you solve that, how do I fit my family of distributions that I've chosen, so if they're multivariate normals, for example, how do I fit a normal distribution to this sample? And the sample you're fitting it on is the elite set, the ones that are pushing closer to the rare event. So there's a little hitch to it, though, is that it's not a pure maximum likelihood, but you have to weight some samples more than others. And the weighting factor, the weighting that you apply is this likelihood ratio, the original density divided through by the density of the previous proposal density. Round 3. So all of these details are the same, except I've written out exactly what this means for the weighted maximum likelihood step here. So at this point, you've got one proposal density from your previous iteration. You've figured out which are the elite samples, and you want to choose the V which maximizes this distribution. This function here. So this is a sample average over all of the ones that all of the R replicates that you have. But this indicator here, the XR greater than gamma I, that means that you're only really summing over that elite set that I mentioned before, the sum of all the, how would you write that? All of the XR that are inside this elite set. That's effectively, this indicator is killing all of the ones that didn't perform well enough. Here is that weight that I mentioned, the likelihood ratio, and then the log likelihood. So just writing that in a different format, if you didn't want to maximize, but you wanted to set the derivative of that to 0, this is what you would get. The derivative of this thing, so it's almost all the same. The indicator comes across the likelihood ratio, and then you just have the derivative with respect to the parameter V inside there, all set to 0. So let's try this for some simple example. So let's say that we're looking at exponential distributions, and we're saying that the density, the family we care about, f given theta, that is just 1 on theta e to the minus x on theta. So that's sort of working backwards. Theta is the expected value of this exponential distribution. So let's say that we're halfway through the cross-entropy method. We've got some proposal exponential distribution with the parameter vi minus 1 from the previous iteration. We've sampled from that distribution capital R times IID, and we want to solve this with this thing, which is setting that derivative to 0. So what does that look like? So this part in here is really the part that needs simplifying. ddv of the logarithm of this. So what do we get? We get log of 1 on theta minus x on theta. So bring the derivative through, ddv, these should be v's, not thetas. 1 on v, x on v. So ddv of log v inverse minus ddv of x v inverse. So what do you get here? The derivative of the log, 1 on whatever's inside the log, and then multiplied by the derivative of what's inside the log. Subtract out this one, you bring the minus down, becomes a plus, and subtract 1 from the exponent. So what's this become? This thing simplifies to just v times this derivative here. So minus 1 on v squared minus, where am I? X on v? No. Oh yeah, x on v squared. And then this v cancels with the square, and we have now, did I get that right? 1 on v minus 1 on v plus x on v squared. Okay, that looks like it worked. So plugging that into the formula we had before, this is the thing we're trying to maximize. So we've set its derivative to 0. That's what this equation says. And then instead of the grad v log f xr v, we put in the real value for that, which is for the exponential distributions. And then we can solve this algebraically. So this part we can split up. So we can take this to one side and then the other part to one side. So the sum of the indicators of the xr's being greater than gamma, f of xr on f of xr given the previous proposal multiplied by xr, and I'll bring this 1 on v squared to the front. Sorry, 1 on vi squared equals, and then almost the same thing on the other side. Sum from r equals 1 to r, indicator xr is greater than gamma, then this likelihood ratio. And then again, I'll bring the 1 on vi to the front. So we can multiply both sides by 1 on vi squared. Multiply both sides by vi squared. So that'll cancel out over here. This 1 on vi will turn into vi. And then you finally get, after all this, your update is that vi is sum from r equals 1 to capital R. Let me see if I can make this computer run a bit faster. So sum over the indicator xr is greater than gamma this likelihood ratio multiplied by XR. That whole thing divided by the same thing without the XR. Whew. So that probably looks absolutely disgusting to you. And but maybe if we can compare it to something simpler, it'll look nicer. Actually, my computer's going crazy right now. I don't know why. So imagine if you just had the situation where you wanted to do a maximum likelihood estimate for an exponential distribution. You just had x1 up to xr, and you wanted to find what's the best exponential fit you can get for that. Well, the mean of that fit that you would give is just, you'd sum over each of the data points, and then you just divide through by how many. Your maximum likelihood estimator mean would just be the sample mean. So let's take it a little bit further. Let's say that you wanted to weight some points so that they're more important to you than others. You want the fit to favor, I don't know, maybe the points, the later points rather than the earlier points. Then the way you would do that is you would give weight to them by throwing in a WR here, and then instead of dividing through by R, you divide through by the sum of those weights. So is this starting to look a bit closer? So that's how you do a weighted maximum likelihood estimate. And the only difference here is that we have this indicator saying that we're only going to pick up the x's that are in the elite set.